Hello, 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 and welcome to another episode of Mr. Boskin Does Some Math. Today we're doing Illustrative Math, Grade 8, Unit 2, Lesson 8 practice problems. In each pair, some of the angles of two triangles in degrees are given. Use the information to decide if the triangles are similar or not. Explain how you know. Well, we know that if a triangle has an angle of 53 degrees and another one of 71 degrees, those three angles have to add up to 180 degrees. So if we do 180 subtract 71 subtract 53, the other angle has to be 53. No, 56. Hey, Mr. Boskin, type in the equal sign. Isn't it nice to know that you aren't the only one who makes mistakes? I'll even double check. 180 subtract 53. 127 subtract 71 is 56. Now, triangle B, we know, has an angle of 53 and an angle of 71, which means this one must also have a 56 degree third angle, which means those two triangles have to be similar to each other. Okay, next we have a 90 and a 37 and something else. What's that something else have to be? Well, they have to add up to 180. So if I take away that 90, that leaves us with 90 more. Subtract 37. Ooh, that last angle has to be 53. On this triangle here, we have a 90 and a 53. And if we look at this first one, we know that if we have a 90 and a 53, the other angle has to be 37. So this one must have a 37 degree other angle. So those two triangles are similar. Those two triangles are similar. Let's try one more. Triangle E. 63 degrees and 45 degrees. So they have to have a sum of 180. If I subtract that 63 degrees, that leaves us with 117. Subtract 45 more, this other angle must be 72. Well, if this one's 63, 45, and 72, this one's 14, 71, and something else. Do we even care what the something else is if neither of these match any of these three angles? No way, Jose. Those triangles are not similar to each other at all. Now, this one, we know we have one angle that's 121 and two other angles. What are they? I don't know. Maybe one of them 70. What's 121? So now we'd have to figure out if we have a 70 to match this one. Let's figure out what this other angle would have to be. They have to add up to 180. I subtract 121. That's 59 degrees. Subtract that 70. That's negative 11 degrees. Does it make sense to have a triangle with angles of 121 degrees, 70 degrees, and negative 11? That's a mess. There's no way we can have a 121 degree angle and a 70 degree angle in the same triangle, because just those two makes more than 180. Those two are not similar to each other. Okay. Next question over here says draw two equilateral triangles that are not congruent. We're going to call those angles the same, those sides congruent, and now I'll do another one. I'm going to say those angles are all congruent to each other. These sides are all congruent to each other. Measure the side lengths and angles. Are the two triangles similar? Well, I'll do it simple and say that each one of those is 1 inch long. Each of those is 2 inches long. Are the two triangles similar? Yes, because even without measuring these angles, if they're equilateral, all the angles have to be the same. They have to add up to 180 degrees, and 180 divided by 3 is 60. So all the angles are 60. Are there two triangles similar? Yes, they are. Do you think two equilateral triangles will be similar always, sometimes, or never? Well, we just talked about that. If they are equilateral, all three angles are the same. 180 divided by 3 is 60. They are always going to be similar to each other. Because equilateral triangles always have three 60-degree angles. Oogly doogly, what is next? In the figure, line BC is parallel to line DE. Explain why ABC is similar to ADE. Ooh, parallel lines. We love us some parallel lines. We know with two parallel lines and a transversal that corresponding angles have to be congruent to each other. That means this angle here and this angle here have to be congruent to each other because of our parallel lines. Those two lines are parallel. The corresponding angles on the transversal have to be congruent to each other. Ooh, we've got ourselves another transversal. That means that this angle and this angle have to be congruent to each other. And if we know this angle and this angle are congruent to this one and this one, ooh, these are both the same angle. That means all angles are congruent to each other. Why are they similar? All angles are congruent. That U did not show up very well. There's a tiny little U in there. The quadrilateral PQRS in the diagram is a parallelogram. Yep, that looks like a parallelogram. Let PQRS prime be the image of PQRS after applying a dilation centered at point O, which is not shown. So we know there's some O. We know there is a scale factor of 3. Which of the following is true? P prime Q prime equals PQ. PQ and the new PQ prime, are they going to be the same? Not with a scale factor of 3. PQ prime is 3 PQ. So however long PQ prime is triple what PQ is. Well, if we scale it up with a scale factor of 3, the new one, the image, is going to be 3 times bigger. So yes, the length of the new one will be 3 times the length of the old one. Next question here says PQ equals 3 PQ prime. So is this original going to be 3 times as long as the new one? Well, scale factor of 3 means we're making the new one bigger. So the old one's not going to be 3 times bigger. That doesn't work. Cannot be determined from the information giving. Hey, we got one of those as being true. That's not it. It's B. Which of the following is true? B. Ooh. Describe, I like describing, a sequence of transformations for which quadrilateral P is the image of quadrilateral Q. So how do we turn Q into P? How do we turn Q into P? Well, I think this is going to require rotation. But do I want to rotate it first? Do I want to translate it first? Because rotating it alone, especially if we use our nice, easy to do center of rotation as the origin, that's not just going to be a rotation. So let's rotate and translate separately. Well, if I rotate Q up to where P is, it's 12 units away from the origin. This end of Q is 12 units away from the origin. Let me zoom that in a little bit so you can see better now. I haven't got 12 units up here, so let's translate it first. Well, P is 1 unit away from the x-axis, which means I'm going to want Q to be 1 unit away from the y-axis. So the first thing I'm going to do is close this calculator so I've got space to write. I'm going to translate Q. So that's 7, and I want it 1, 6 units to the left. That's going to, if I move this point here 6 units to the left, it's going to be right there. If I translate, well, I'm going to do this in a different color so it shows up a little better. Those 2 points. If I translate this point 6 units to the left, 10 is going to go to 4. If I translate this point right here 6 units to the left, 10 is going to go to 4. And now this bottom point here, 6 units to the left, 12 is going to go to 6. That gives me my 4 points of this quadrilateral. Okay. I'll call that Q prime for now. We translated 6 units to the left. Now, I'm going to want to rotate around the origin, because I always like to rotate around the origin. It makes the work a little bit easier. If I take this Q and rotate it 90 degrees around the origin, this vertex right here, which was the point 1, negative 4, will become the point 4, positive 1. Ooh, that works out pretty nice, doesn't it? Now, this vertex here, which is at 4, -4, will become 4, +4. 4, -3 will become 3, +4. And 6, -6 will become 6, 6. Those vertices seem to work out pretty nice. So we rotate around 0, 0. You're probably yelling at me for not telling you we're going 90 degrees. Counterclockwise. So we do that first. We do that second. And that takes Q and puts it exactly on P. That's the last one. This has been another episode of Mr. Boskin Does Some Math. Thanks for watching, and I'll see you next time.